Hi. In this recitation, we're going to talk about non-asymptotic hypothesis tests for the mean of Gaussian random variables. You will recognize the setup in this recitation. It's similar to what we've done before, but the crucial difference will be that we want to come up with tests that are non-asymptotic and do not only hold in the infinite sample limit n going to infinity, but for finite samples. And you will recognize that the tests are very similar to what Philippe already showed you in class, especially under the name t-test. But we want to just go through the justifications necessary to arrive at the t-test in a little bit more detail. So what's the setup? Let's think about observing n random variables that are Gaussians with unknown mean mu and unknown variance sigma squared in their IID. In order to be explicit, one example you could think about is you are developing a new drug, let's say, to lower a patient's blood pressure. Now, you administer that drug to a couple of samples, to a couple of people, 1 to n. And we are simplifying a lot here, and we're just assuming that the response of every person, so let's say xi actually records the difference of blood pressure before and after administering the drug. And let's say every person responds the same on average to this drug, and the only fluctuation that we see can actually be modeled as noise, and especially as Gaussian noise. Okay? And now our goal is to and those are both unknown, I forgot to say. Our goal is to test the hypotheses. So let's say, remember, if I run a hypothesis test, I always have a choice. What do I call null hypothesis and what do I call alternative hypothesis? And in this case, I want to test, is my drug actually effective? Does it lower blood pressure? And a lower blood pressure would correspond to a negative mu. But in this case, since I want to actually prove that it lowers blood pressure, that should be the alternative hypothesis. Why? Because I want to be able to actually reject the null hypothesis. And the null hypothesis consists in the drug either keeps the blood pressure constant or actually raises it. And we want to test this with level alpha. And again, I'm looking for a non-asymptotic test here. How are we going to do this? We're going to go through the same steps as before. First, we're going to estimate mu. And since you already should have the intuition that if I try to turn an estimate of mu into a test statistic, then probably sigma squared will show up somewhere. So that means I will also have to estimate sigma squared. Once we're done with this, we're trying to write down a test statistic, or more generally, a pivot function that depends on mu and sigma squared. Okay? And point number 2 will be where the main hard work of this recitation will lie, because now if we want non-asymptotic tests, we'll have to understand the exact distribution of, or at least have very good bounds on the exact distribution of our estimates. And this is possible in the special case where our observables are actually Gaussian random variables. And finally, so this will lead to a test psi where we take the indicator function of the test statistic exceeding a certain level s, and then we will adjust s to match the desired level alpha. As a quick warm-up, let's do step number 1. And we'll make our lives easy and just say, let's take the maximum likelihood estimator for mu and sigma squared. Now, remember, so and I'm abbreviating with MLE, maximum likelihood estimator. Remember, how does that work? I write down the likelihood for observing the data x1 to xn. Let's call it f, depending on mu, sigma squared, and x1 up to xn. Now, I have IID data, so this is going to be a product from I to n of the likelihood of each individual xi. And this is Gaussian, so the density has a normalization factor, 1 over square root 2 times pi times sigma squared, times exponential of minus 1 over 2 sigma squared xi minus mu squared. OK, and now, given my samples x1 to xn, I want to maximize this with respect to mu and sigma squared. It's often easier, and this is no exception, to do this on the log level. So let's write down the log likelihood, L. And I'm going to omit the dependence on x1 to xn. That should be understood implicitly. This is going to be log f. Now, what happens if we take the log of this expression? Well, the product becomes a sum. Then this product between the prefactor and the exponential also turns into sum. And furthermore, here I also want to take this apart. Let's make big brackets here. This is going to be 1/2 of the square root of log 2 pi minus 1/2 log sigma squared, minus because it's in the denominator, minus, so logarithm of exponential becomes identity, 1 over 2 sigma squared xi minus mu squared. OK, and I can rewrite this because this does not depend on the xi. This just appears n times. And you already see that the first term does not depend neither on mu nor on sigma squared. So this is not going to enter the calculation of maximizing it. Similarly, we have n over 2 times log sigma squared. And finally, we have 1 over 2 sigma squared. And here we still have a sum of the squares xi minus mu. OK, so in order to maximize it, this is going to be a smooth function. So let's just compute gradients, or rather partial derivatives with respect to mu and sigma squared, and set them equal to 0. So let me start with the partial with respect to mu. Now, this term does not depend on mu, neither does this term. So the only thing that remains is that one, minus 1 over 2 sigma squared times the sum. And then I have to differentiate the square, which gives me 2 times xi minus mu. And then because it's minus mu, I multiply this by minus 1. OK. And I set this equal to 0. And yeah, so remember, I can set this equal to 0 even if I don't know sigma squared yet, or I don't know the maximizer sigma squared yet. Why? Because sigma squared is going to be larger than 0, in particular not equal to 0. So I can just multiply by this quantity here, and we have something that only depends on the xi's and mu. So we can actually already solve for the optimal mu, and we're going to call it mu hat. Mu hat is going to be, you see, I'll have n times mu coming out of the sum. So bring this to the other side, I'll have 1 over n times the sum over the xi's. So the maximum likelihood estimator for mu is just going to be the sample average. And let's write that here already. Great. And now differentiating with respect to sigma squared. Remember, I want to treat sigma squared often as a variable in its own right. So whenever I write sigma squared, think about it as another variable, let's say y. And I'm not really caring about the squared here. So here I'm not differentiating with respect to sigma, but with respect to sigma squared. Since for positive numbers, this is a bijection, it doesn't really matter what I do or how I do it, but this is often a little bit prettier. OK. Looking at this again, this is a constant. This term here has derivative 1 over sigma squared for the logarithm. So it's minus n over 2 sigma squared. And this one here is something like 1 over x, which has derivative minus 1 over x squared. Minus times minus gives me a plus. And I end up with 1 over 2 sigma to the 4th. And the sum of the squares. Now, if I set this equal to 0, you see I can multiply through by sigma to the 4th. So there's no sigma dependence in this term and only a sigma squared here, which means sigma squared hat, or sigma hat squared, is going to be, again, dividing by n, just the sum over these squares. And now I have to plug in the optimal mu that I already found. So this is going to be xi minus mu hat squared. And we can copy it here. So this is the average over the squared deviations, over the squared errors, basically. OK. So this was something you probably had seen before. But now we're trying to turn these estimators into test statistics on the next Blackboard. First, I'll have to erase. And while I'm doing this, you can think about two things. How about you calculate the expectation, or remind yourself what the expectation of sigma hat squared is? And secondly, I was cheating a little bit. I was just setting the derivatives to 0 here. I did not exactly justify to you why mu hat and sigma hat squared are global maximizers of the likelihood, but you can think about this.